Hello students, welcome you all. In my today's lecture, I will start the topic spectroscopy, and in spectroscopy we will see various spectroscopic techniques like UV visible spectroscopy, then NMR spectroscopy, IR spectroscopy, and mass spectrometry. So these all spectroscopic technique, it gives us the information about the structure of any unknown molecule. So we can determine the structure of any unknown molecule if we have a different spectral data which is coming from UV visible or IR or NMR or mass spectroscopy. So if we combine all these data, if we have all these data, and then we can get the information of, we can determine the structure of any unknown molecule. So suppose if you are given any problem, a spectroscopic problem to find the structure of any unknown molecule, then in that problem you will be given a molecular formula. Usually a molecular formula is given to you, and some spectral data are given, spectral data from which is coming from the UV visible or NMR, IR and mass spectrum. So if we interpret that data, after interpreting that data, and then you can get the molecular structure. But suppose if a molecular formula is given in that problem, then our first step is to determine the double bond equivalent. Our first step in spectroscopic problem is to determine the double bond equivalent, and which is also called as the index of hydrogen deficiency, DBE or IHD. It is index of hydrogen deficiency, or it is also called as the degree of unsaturation. So here in this lecture we will learn how we can determine the degree of unsaturation, what is its formula, how can we determine it, and why it is called as the index of hydrogen deficiency, and we will see some more about this formula. Okay, so this index of hydrogen deficiency or this degree of unsaturation, it gives what it gives the first, it is the first step to determine the molecular structure of any unknown compound. So, or we can say this gives you the clue, it gives us the clue to determine the molecular structure. So like in spectroscopic, various spectral data are there, and they give us a clue to determine the molecular structure. So this is the first step which give us clue to determine the molecular structure. It is the first step to determine the structure of unknown compound. Unknown compound. Okay. So how can we determine this degree of unsaturation? We can determine by using the formula. So this also tells you that as this unsaturation means double bond. So it gives you the information about the number of double bond or number of unsaturation, or we can say it gives us the information about the multiple bond. So one thing, it gives you the information about the multiple bond as well as the number of rings. So the much better definition is it tells you the sum of number of, it gives you the information of the sum of multiple bond and ring in the structure. So it tells about the sum of pi bond and rings in the structure. In the we can say molecular formula, or we can say if a given molecular formula is given, if any molecular formula is given, then in molecular formula it tells you how much pi bond and rings are present, or the sum of pi bond and rings. So this is the important one. It tells you the sum of pi bond and rings in the structure. It does not give you the individual information of number of pi bond or number of rings. Okay, so it only gives you the sum. It tells the sum of pi bonds and rings in the structure. So what is the formula? So if we have, suppose, DBE, the formula for DBE, or we can say index of hydrogen deficiency. So this is equal to 2 multiplied by number of carbon atom plus 2, okay, plus number of nitrogen atom minus number of hydrogen atom minus number of halogen atom divided by 2. So this is the formula to determine the DBE, or we can write it as C plus 1 plus N by 2 minus H by 2 minus X by 2. So by using this formula we can determine the number of double bond, or we can determine the sum of double bond and rings in the given molecular structure. Okay, so this is the formula. Now, so suppose, let us take one of the example. So if a molecular formula given, is C6H6. C6H6 is the molecular formula which is given in a problem. And suppose if we want to find the molecular structure of this given molecular formula. So all of you know the C6H6 is a benzene ring. C6H6 is a benzene. Okay, but what is the exact molecular structure of this C6H6? That can only be determined if we determine the DB, as well as if we interpret the spectral data, that is IR data, UV data, NMR data, and this mass spectral data. Then only we can determine what is the exact structure of this C6H6. Because this C6H6 is not only the benzene, C6H6 may also have some other structure. So how? So first of all, I will calculate the DBE. So DBE, this is equal to 2 multiplied by number of carbon atoms 6 plus 2 plus number of nitrogen atom is 0, number of hydrogen atom is 6, number of halogen atom is 0, divided by 2. So this is equal to 12 plus 2 18, 18 minus 6 12, 12 by 2, that is, it is 12 by 2, and it comes out to be 6. It comes out to be, 12 plus 14, 14 minus 8, and it is coming out to be 14. It is 12 plus 14 and 8, so 8 by 2, it comes out to be 4. So double bond equivalent, or index of hydrogen deficiency is coming out to be 4. So according to this definition, this DB is the sum of pi bond and rings. So this 4 is the sum of pi bonds and in the ring. So either this 4 may be only ring may be present, only 4 rings may be present. So one of the possibility is that this 4 may be 4 rings, either 4 rings may be present, or if it may have 3 rings plus 1 double bond. Next possibility, that 2 rings may be present. 4 corresponds to 2 ring and 2 double bond, and 4 may corresponds to 1 ring and 3 double bond. 1 ring and 3 double bond. Okay, so now, so if it has 1 ring and 3 double bond, then one of the possibility that this corresponds to the benzene ring. This is, in this benzene ring we have this one ring and 3 double bonds. This is the 3 double bond. Okay, now if it is having 2, if this 4 corresponds to 2 ring and 2 double bond, then what it may correspond? It may correspond to the structure like this. Okay, this is, now this corresponds to 2 ring. So how many bonds are present in this benzene? Total bonds. Total bonds is, this is 6 single bond and 3 double bond. 9 bonds are present actually. So here also, if you will see, then how many bonds? 7 bonds, 8 bonds and 9 bonds. So this is the Dewar benzene. So this C6H6 here may also correspond to the Dewar benzene. It may, suppose if we have other spectral data, then after interpreting other data, then we will decide whether the C6H6 is benzene or if it is, this is the Dewar benzene, whether this Kikuyu structure or this Dewar structure. Okay, so it may, we may also represent this one as like this. We may also represent in this way also. Same structure can be represented in this way. These are the 2 rings and then 2 double bonds. This is another way of representing the same structure. Okay, or otherwise we may also represent it in this way also. We may represent in this way also. So different way of representation. When the total 9 number of bonds are present, then we can represent in different way. And now if it is having 3 rings and 1 double bond, 3 rings and 1 double bond, so we can represent this one as okay. So this is one of the ring. Okay, second ring, this is our third ring. So 3 rings and plus 1 double bond. This is another way of representation. Okay, so 9 bonds are, total 9 bonds are present, 3 rings and this, or we may also represent it in this way also. We may represent in this way also. This is 1 ring, this is now 2 ring, and this is your 3 ring and 1 double bond. So this is called as a benzoline. This is structure is the benzoline structure. Or otherwise we may represent it in a, when 4 rings are present, when only 4 rings are present, then we can represent it in this way. The 4 rings can be represented. Okay. Okay, so we may represent in this way. These are the 2 rings, and then this is one of the 3-membered ring, and this is another 3-membered ring. So here we have the 4 rings only. So what I mean to say that this double bond equivalent, the value which is coming out from this double bond equivalent, this is the sum of pi bonds and ring. So this does not tell you whether it does not tell the individual value of pi bonds or the individual value of rings present in the structure. Okay, so this is about this thing. Now we will discuss why it is called as the index of hydrogen deficiency. Okay, now so let us see more about this formula. So we will discuss more about this formula now. Now suppose if we have any hydrocarbon which does not contain any double bond. So we will see, we will take a case when hydrocarbon is not having any double bond or ring. Hydrocarbon having no double bond or ring. There is hydrocarbon. It means, what does it mean? It means that it may be a simple alkane. The hydrocarbon may be simple alkane like C2H6. In the same way, we can suppose we have this C4H10. This corresponds to C4H10, butane, ethane. And in the same way, suppose it may have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So total number of carbon atom here is 10. So this corresponds to the formula C10H22. This corresponds to C10H22. Now in this formula, so number of hydrogen atom, if you will see. So how many hydrogen atom is present? So number of H atom, this is equal to 2 multiplied by number of carbon atom plus 2. Okay, so number of hydrogen atom is 2 multiplied by number of carbon atom plus 2. This is the number of hydrogen atom. Now, this is the case when there is no double bond or ring present in any given structure. Now, let us take second case when hydrogen, or sorry, not hydrogen, this is hydrocarbon. This is hydrocarbon. Hydrocarbon having no double bond or ring. Now, suppose if we have a hydrocarbon having only double bond. Now let us see this case. Now, so this is one of the hydrocarbon which is having only double bond. This is one of the case. One double bond is present over here. Okay. Now this is the case when one double bond is present. This is the another case when two double bonds are present. So what is the formula for this? The formula for this is C2H4. Here, what is the formula for this? The formula for this is C4H8. And what is the formula for this? It is C4H6. So what we can see over here. Now, if this is the formula of ethane, which is C2H6, and this is the formula of ethene, this is C2H4. If there is one double bond, then hydrogen decreases by 2. In the same way, if one double bond is reducing the number of hydrogen by 2. Another double bond is again reducing the hydrogen by 2. So what we can see that each double bond reduces the hydrogen count by 2. So what we can write, each double bond reduces the hydrogen count by 2. Okay, and this is called as the hydrogen deficiency. This is called as the hydrogen deficiency. If the double bond is present in the given hydrocarbon, then hydrogen deficiency would be there, or the hydrogen count that will decrease by 2. So this is called as index of a hydrogen deficiency. So that's why the degree of unsaturation or double bond equivalent is called as the index of hydrogen deficiency. So now you should clear why it is called so. Okay, so this is the case when double bond reduces the hydrogen count by 2. But in a beginning, I gave you the definition that the double bond equivalent or DBE is the sum of double bond and ring, the sum of double bond and ring. So double bond is reducing the hydrogen count by 2, and let us see whether the ring also reduces the hydrogen count by 2 or not. So let me take the case third, when hydrocarbon having only ring in the structure. Okay, hydrocarbon, third case, hydrocarbon having ring only ring is present. Okay, so if I take the example for this, now suppose this is the one of the case. So 5 carbon atom is there, and the molecular formula for this will be C5H12. C5H12 is the molecular formula. Now suppose I convert this C5H12 into a ring. Now I have converted into ring. Number of carbon atom remains same over here, so I have converted into ring. So now the molecular formula will become C5H10. It is cyclopentane. This is pentane, this is cyclopentane. So if double bond, if one of the ring also reduces the hydrogen count by 2, and we can see other case also. We can see, suppose we have hexane having the molecular formula C6H14, and now if I convert it into the ring, then what is its molecular formula? Its molecular formula, all of you know, cyclohexane having the molecular formula C6H12. In the same way, suppose I write this structure. So how many carbon atom over here? Number of carbon atom, if you will see, this is 10 carbon atom. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the molecular formula for this is C10H22. C10H22. Now, what would be the, suppose I convert it into the rings, and suppose I convert into the ring, and it becomes 2 ring. Now it has been converted into 2 rings. Then if you count the hydrogen, number of hydrogen atom, number of carbon atom is 10, and number of hydrogen atom, it is here 18. And this is the structure of decalin. This is the structure of decalin. So what you will see here, what you can see over here. Here you can see that if 2 rings reduces the hydrogen count by 4, one ring reduces the hydrogen count by 2, and another ring is reducing the hydrogen count by 4. Okay, so the same thing is there. Double bond reduces the hydrogen count by 2. In the same way, the ring also reduces the hydrogen count by 2. Now another, if you take next example, suppose if I have 1, 2, 3, 4, 5, 6, 7, 8 carbon atom, and this 8 carbon atom, that can be represented like this also. So here, so this is how many? C8H18, and this is C8H14. 2 rings. Again, if each ring is reducing the hydrogen count by 2. So this is the case. So what we have discussed? We have discussed the case where hydrocarbon is having no double bond or ring. If hydrocarbon is having double bond, it reduces the hydrogen count by 2. If hydrocarbon is having the ring, it also reduces the hydrogen count by 2. And now suppose I take a case when a hydrocarbon contains a double bond as well as the ring. So next case, hydrocarbon having double bond as well as ring. So in a same structure, we have double bond as well as ring. Now let's see this one. So what you can see, suppose I have 1, 2, 3, 4, 5, 6. Now, so this is the structure of hexane. And now suppose I put a one double bond over here. If I put one double bond over here, then this corresponds to structure. This is, what is this? What I told you. This is C6, because 6 carbon atom is there and one double bond is there. Then it would be C6H12. This is C6H12 because hexane is C6H14, and if one double bond is present, then it is C6H12, and this structure is also C6H12. So suppose if C6H12 is there, then it may be hexene or it may be cyclohexane. Both possibilities there. So both are C6H12. Now suppose I put one more. Suppose I put one more double bond. Then what would be the molecular formula? The molecular formula will be C6H10. C6H10. Okay, 2 double bonds, and this also corresponds to a cyclohexene. So this formula, the cyclohexene, it also corresponds to C6H. So in this structure, if you will see, in this structure we have a double bond as well as ring. So if we will find the double bond equivalent from here, so let us find the double bond equivalent for this. The double bond equivalent, this is equal to 2 multiplied by 6 is equal to 12 plus 2, okay, minus number of hydrogen atom. So because there is no nitrogen atom, no oxygen atom, so I have only written for hydrogen atom, divide by 2. So it is 14 minus 10, that is 4 by 2. 4 by 2, that is equal to 2. So double bond equivalent for this is coming out to be 2. So if double bond equivalent is coming out to be 2, it means either it may have 2 double bond or it may have 1 double bond and 1 ring. Okay. In the same way, suppose I write another structure and suppose 3 double bonds are present. Suppose 3 double bond is present, then it is C6H8, and this corresponds to the structure. This one. Or we can write this corresponds to the structure like this. Either the conjugated double bond will be there or non-conjugated double bond may be there, and that can only be determined from the other spectral data. Okay, from other spectral data. So this dB only tells you whether the double bond and rings are present. So here this C6H8, this is also C6H8, and this C6H8, it means either it may correspond to 3 double bond or it may correspond to 2 double bond and 1 ring. Okay, so it means if you will find the double bond equivalent, then it comes out to be 3. For this, the dBe, here the dB comes out to be 3. Here dBe is 2. Here dB is 3. So this is the case. Now suppose another case. Let us take the Next case, 1 double bond, 2 double bond, and suppose I put a triple bond over here. So how many pi bonds are there? Number of pi bonds in this structure. So what is the molecular formula for this? The molecular formula for this will be C6H6. One more double bond, it will reduce the hydrogen count again by 2. So here this is C6H8. I have put one more double bond, one more multiple bond, then hydrogen count will decrease by 2. So this is C6H6. So this C6H6, so if you will find the double bond equivalent for this, then it will come out to be 4. So 1, 2 pi bond, 3 pi bond, 4 pi bond. So 4 pi bonds are there. So this C6H6, it also corresponds to the benzene. It also corresponds to the benzene ring. Either this is the case, or I have given you the other structure for this C6H6 previously. It may be divar benzene, it may be benzoylene, it may be prismane. So like this. So this is the case. So if and double bond equivalent is 4 over here. So what I mean to say that this DBE, it tells about the sum of double bond and ring in the given structure. So this I have discussed the hydrogen deficiency, about the hydrogen deficiency. Each double bond is reducing the hydrogen count by 2. Each double bond is reducing the hydrogen count by 2. Now, so in structure, in the formula, we have also nitrogen atom, we have also the halogen atom also. What was the formula? The formula was, this was the formula, the DBE, this was equal to 2 number of carbon atom plus 2 plus number of nitrogen atom minus number of hydrogen atom minus number of halogen atom divided by 2. So we have seen about the carbon atom, if carbon is present in the formula and hydrogen is present in the formula. What about the halogen? So halogen works same as the hydrogen. So hydrogen is monovalent atom, and halogen atom like chlorine, bromine, fluorine. So this is also a monovalent atom. So monovalent atom, it reduces the hydrogen count by 2. As the hydrogen atom, as the double bond reduces the hydrogen count by 2, in the same way double bond also reduces the halogen count by 2 also. Double bond also reduces the halogen count by 2. How? So if I take the example of this ethane, that is C2H6, and now suppose I replace it with fluorine atom. Suppose I replace it with this fluorine atom, and suppose hydrogen, and I replace it with 6 fluorine atoms. And if we put a double bond, then 2 fluorine atom, number of fluorine atom, that will reduce by 2. So double bond also reduces the number of halogen atom. Similar to the number of hydrogen atom, double bond also reduces the number of halogen atom. Now what about the oxygen atom? Whether the oxygen atom, if double bond can reduce the number of oxygen atom? So let us see. So if we have suppose this pentane, and if we put this double bond over here, and 2 double bond is present in this ring, and now if I put a oxygen atom in this structure, so oxygen atom doesn't affect the DBE value. Oxygen atom is not affecting the DBE value. Here you can say fluorine atom is affecting the double bond. The double bond reduces the number of fluorine atom, but double bond is not affecting the oxygen atom, or we can say presence of oxygen atom does not affect the DVE value. Now suppose if we have a nitrogen, what about this nitrogen atom? If we have a, suppose, hydrazine N2H2. Okay, so now in this case, suppose I put a double bond. I put one more bond. Okay, so number of pi bond is 2. Then the double bond is reducing the hydrogen atom. So we have to remove this 2 hydrogen atom. So that's why this nitrogen atom, hydrogen atom, and halogen atom is affecting the dBe value, but oxygen atom doesn't affect the dBe value. That's why the oxygen atom is not present in the formula. Now let us take one or two examples. Suppose if we have a structure having oxygen atom, and suppose if we have aspirin. We have a aspirin, one of the acid functional group, another ester functional group is present, and the molecular formula for this is 6, 7, 8 carbon, 9 carbon atom is present, and hydrogen atom 1, 2, 3, 4 and 5, 8 hydrogen atom is present, and number of oxygen atom is 4 over here. So if you are determining the dBe value, dB comes out to be 2 multiplied by 9, okay, number plus 2, no nitrogen atom is present, hydrogen is 8, and oxygen is not present in the dBe structure. Okay, so this divided by 2. So 18 plus 2, 18 plus 2, 20, 20 minus 8, 12, 12 by 2. It comes out to be 12 by 2, and this is 6. So this 6, this corresponds to 1 ring, and 1, 2, 3, 4, 5 double bond. So 1 ring plus 5 double bond. This is the case. So as you can say, we have not taken the oxygen in the formula, and without taking this oxygen in the formula, we are getting the correct dBe value, correct things. In the same way, suppose if we have a molecular structure which contains the nitrogen atom and chlorine atom, then here the molecular formula, if you will write the molecular formula, and how many carbon atom? Carbon atom is 5 carbon atom, hydrogen atom 2, 4, 6, 8 and 9, 10 hydrogen atom, 1 nitrogen atom, 1 chlorine atom is present. Okay, so dBe, if you will find, so dB comes out to be 2 multiplied by 5 plus 2 multiplied by 5, okay, and plus 2 and plus 2. Number of nitrogen atom is 1, hydrogen atom is 10, halogen atom is 1, divided by 2. Okay, so this is the case. So 10 and 12 and 13. 13 minus 11 is 2. So this is equal to 2 by 2, that is equal to 1. So this 1 dBe value, it corresponds to 1 ring. So 1 ring is present over here. So 1 ring is present in the, this is the possibility, the 1 ring is present. Okay, either 1 ring or 1 double bond, and that final this structure that can be determined by the other spectral values. So this is about the dB or double bond equivalent or index of hydrogen deficiency. Thank you.